This video is going to look at two more examples of balancing using oxidation numbers. So the oxidation numbers are in here already, but I'm quickly going to go through why they are what they are. So remember that in elements like aluminum and hydrogen, they're not sharing or transferring electrons with anything else, so their oxidation state will be 0. Oxygen's usually -2, so in water it's -2, in hydroxides it's -2, so it's -2 everywhere here. Hydrogen is, when it's in a compound, usually +1, so we've got a bunch of hydrogens that are +1. The sodium in sodium hydroxide is a monatomic ion, and it's likewise a monatomic ion in this somewhat more complex substance here, the aluminum sodium hydroxide, and the aluminum is also acting as a monatomic ion. So this is a little bit of a weird compound in that we have two cations combined with a given anion, but they are still their monatomic cations with their corresponding charges. So when we're using oxidation numbers to balance, the first thing we need to do is identify what's changed. Well, we can see aluminum is going from 0 to +3. So that is an oxidation, and it's 3 electrons per atom. So those 3 electrons per atom, we can see we've got 1 atom on this side and 1 atom on that side, so that's why I multiply by 1 atom. It's 1 atom on both sides. What else changes? Well, this is a little trickier, but we can see that the hydrogen all starts out as +1, but some of it ends up as 0. So the hydrogen changes, but it's not all of the hydrogen. So I'm only highlighting it on the one side where I can see that's the part that for sure has changed. We don't know which of these hydrogen atoms went into the hydroxide over here versus which of them went into the hydrogen. So we can say that hydrogen is reduced, so it's going from +1 to 0, so that's 1 electron per atom. And we're going to focus on those 2 atoms on the product side. And actually, let's make my highlighting match here. So we'll put our aluminum with the yellow and our hydrogen with the blue. So we've got 3 electrons on the oxidation side, 2 electrons on the reduction side. That does not match. So we need to make it match. Well, if we have 3 and 2, our lowest common multiple is going to be 6, so we're going to multiply to get 6. So the 3 we have to multiply by 2. So we're going to put 2 in there and 2 in there. So that's going to give us a change of 6 electrons on that aluminum. And then on the hydrogen, to get the 2 to be 6, we're going to have to multiply that one by 3. Now this one's a little tricky because over on the other side, well, what do we multiply? Well, some of this hydrogen went here and some of it didn't, so we're going to leave those for the moment. Instead, what we're going to do is we're going to say, well, we know those ones that we've just dealt with, we don't have to mess with again. So we're certain that we have 2 aluminums, 2 aluminum sodium hydroxide, and 3 hydrogens. So we're going to balance the remaining substances so that they match. So I would start with sodium next, because I know I'm not going to mess around with this one. We said this 2 has got to stay, so I've got 2 sodiums. I'm going to have 2 sodiums here. That, oops, kind of messed things up. So we know that one stays the same. So now I can focus on just the water, because I need the oxygen and the hydrogen to match. But I've messed around with every other substance in here, and I know I don't mess around with them twice when I'm using this method. So if I look at my oxygen or my hydrogen, either one, I can figure out how to balance my water. So I'm going to look at the oxygen. So I have 4 oxygens in my substance times 2, so I have 8 oxygens on this side. I have 2 already accounted for in the sodium hydroxide, so I need 6 more oxygens from that water. So that gives me 6 oxygens. If everything worked out right, and it should, my hydrogens should balance. So let's double check that. I've got 2 hydrogens right here, plus 12 here, gives me 14 on the reactant side. I have 4 times 2 hydrogens here, so that gives me 8, plus 6 hydrogens here. that gives me 8 plus 6, 14 on the product side. So 14 hydrogens, 14 hydrogens. So I can now see that this is, in fact, our balanced equation. Second example we're going to look at, again, I'll quickly go over where our oxidation states come from. So we have copper in its metal state. It's an element, it's going to be 0. That's our only element. So then we go to our oxygens are all -2, no exceptions. Hydrogens are all +1, no exceptions. We have one monatomic ion, that's our copper, but be careful, copper has 2 possible charges. So remember, figure out the charge by looking at what it is combined with. So in this case, we have 2 nitrates, that's a total of -2 charges, so the copper has to be +2 to balance that out. The last 2 that we're left with is the nitrogen. They're a little bit tricky. So our nitrogen, on this side, we have to balance that all out, right? So 2 oxygens gives us -6. Plus 1 hydrogen, we're now up to -5, so the nitrogen to balance that out has to be +5. Likewise, in our nitrate ion, we can do that same kind of balancing. -6 from the oxygen, nitrate has to add up to -1, so the nitrogen in the nitrate is +5. And the nitrogen dioxide, a little bit easier because we just have 2 substances, so -2 times 2 gives us -4, so the nitrogen has to be +4 to cancel that out. Once we have our charges, our oxidation states is more correct to say than charges, oxidation states figured out, then we figure out, well, what has changed? Well, we have copper going from 0 to +2. So the copper is oxidized, right? It's increasing in oxidation state, and it's a change of 2 electrons per atom. And we have 1 atom on the reactant side, 1 atom on the product side, so we can just multiply by that 1 atom. The other thing that changes, our nitrogen went from +5 to +4. But not all of the nitrogen did that, because some of the nitrogen is still here at +5. So again, we're going to focus on the part we know changed, so that's going to be the stuff that ended up in our nitrogen dioxide. So we know that's a change, a difference from +5 to +4 of 1 electron. And we have 1 atom of nitrogen in that substance that we're going to focus on the product side. So 1 times 1 gives us 1 electrons. So our electrons aren't balancing out. We need to multiply to get a common value. So the 2 can stay 2, but the 1 we've got to multiply by 2. So we're going to put a 2 in front of our nitrogen dioxide because we're sure that one's changing. And because we're going to know that we're keeping our copper, we're going to put the 1 in front there just to emphasize the fact that it's staying the same. And we're going to put a 1 in front of the copper over here to emphasize the fact that it's staying the same. So we've dealt with the substances that we know have changed in terms of the number of electrons they have. Now we're going to deal with the rest of the substances. So that's only our hydrogen nitrate, or nitric acid if you rather, and our water, which I see has lost its charges. So if we look at those ones, we probably want to focus on the nitrogen first and the oxygen and hydrogen last. So we have 2 nitrogen on this side, plus another 1 nitrogen here. That's a total of 3 nitrogen that we've got to balance with this nitric acid. So we need 3 nitrogen there. And then we need to make out, that is not 3 nitrogen. I just missed, this 2 is here. So we actually have 4 nitrogen. So that's going to be 4 nitrogen on this side to make that balance. And then we need to look at our hydrogen and oxygen. So I'm going to focus on hydrogen this time because I have oxygen all over the place. So let's do our double check with the oxygen. So we have 4 hydrogen here. We only have 2 here. So we balance that with a 2. And then we can double check that our oxygen works out. So 12 oxygen on this side. 6 from here. Plus 4 from here gives us 10. Plus another 2 gives us 12, so our 12 oxygen balances out. So there's two more examples. Hopefully that helps make this a little clearer.